We continue our discussion on classification of data points, and in the last lecture we discussed a classifier called naive Bayesian classifier. In this lecture we will be discussing about another approach of nearest neighbor classification scheme. And here the classification approach is quite simple, as we can see here. In particular, learning algorithm is very simple. What you need to do here, you need to simply store the training data. In compared to the Bayesian classification, you have seen that you need to process the data and perform parametric modeling to get the probability distributions. But in nearest neighbor classification, simply you store training examples, and then prediction algorithm, it goes like this. If you want to classify example by finding the training examples, that is nearest to x. So, which one is the nearest? You assign the class to that sample. So, one particular method in nearest neighbor classification is known as k nearest neighbor method. So, instead of observing a single nearest neighbor, we observe a set of close neighbors, and the k most nearest neighbors are called k nearest neighbors. So, in this case, to classify a new input vector x, we examine the k closest training data points to x, and then assign the object to the most frequently occurring class. So, here the approach is very simple. Let me illustrate with respect to this using this diagram. You can see there are two classes, and their class labels are shown by these two colors, pink and green. And suppose you have a query data point, it is a two-dimensional feature space, and query data point has been shown here. And then for computing the nearest neighbors, you have to compute distances with all the training samples. Nearest means k close neighbors, k most close neighbors. So, you compute distances with all the training samples, and then you should sort them and find out three most closest nearest neighbor. So, you will find that these are the three nearest neighbors. So, that is a technical term that is used there. And and according to the rule what I mentioned, assign the class which has maximum number of nearest neighbors or NNs, and we can see that there are two members from the pink class and one member from the green class. So, we should assign this pink class denoting the pink color to that particular query point. So, this is the approach, and which is very simple to implement and to understand. But there are interesting observations. So, it has a sound theoretical framework, though approach is very simple. We can show that actually it has a good relation with the Bayesian classification rules. So, it is a non-parametric estimation of probability density at x given k neighbors. If I perform these estimations, we will be doing that. So, suppose there are number of training samples n, and we assume the volume, and in an n dimensional space we call it hypervolume containing k neighbors is V, and let us consider the probability of data point in that volume be P. So, following binomial distribution, that means how many data could occur if it's a kind of it could be modeled in this fashion that we are sampling the point, and with probability p it can occur in that volume B, and if we are doing n times this sampling, it follows a binomial distribution, and the number of data points in the volume, expected number could be n into p, and that should be equal to k. So, the estimation of p is very simple. You just get the ratio of k by n, or it is a fraction of times it has occurred out of n trials. So, this is a probability that you can estimate here, and then the probability density at x, if I can consider it is a continuous space. So, this probability is divided by the volume B, that is the number of data points, possible data points there. So, consider a class W1 which contains n1 number of neighbors out of k neighbors, and then the joint probability of x and W1 will be given by that. That means, first the joint probability of n trials, n1 has n1 times that it has occurred within that volume. So, it is n1 by n and then divided by v, that is the density functions. So, probability of x given W1, which is the posterior probability and which is defined from the Bayesian rule, that joint probability divided by probability of x, it is n1 by k. Now, this is the interpretation. If you have n1 neighbors in W1, n nearest neighbors in W1 out of k neighbors, then the n1 by k give you the posterior probability of that class given the data point. So, if you assign the class which for which maximum number of data points have occurred, it is actually the same as maximizing this posterior probability. So, it is following the Bayesian classification rule, as we can see. So, this is what, and it follows the Bayesian inferencing rule. So, when should we consider a nearest neighbor classification? When the instance maps to points in an n-dimensional space, when you have less than 20 attributes per instance and there are lots of training data, then those are the situations when nearest neighbor classification should be more appropriate. There are advantages, as we see that fast training, what means it means that you have to store the data. Of course, you require large storage for that. So, learn complex target functions. The method is very simple, but finally, the functions implicitly it is implemented through this method, that is not simple. So, if you do more detailed analysis, you will be able to understand what are the decision boundaries of k nearest neighbors, and those boundaries are quite complex, their shapes are quite complex, they are not simple. And it do not lose any information. Disadvantage is it is slow at query time, it is very much computation intensive. You have to compute all the distances with all the data points. So, which means your query would be very slow. It is linearly proportional with the number of data points, and if your data point is very large, then it is prohibitively it is very much difficult and easily fooled by irrelevant attributes. So, if there are outliers or rather irrelevant which is not related, but still you are establishing the relationships by neighboring relationships. So, these are the issues like distance measure you have to choose. The most common is an Euclidean distance, and increasing k reduces variance and increases bias, which means class prior dominates in that case. And for high dimensional space, the nearest neighbor may not be close at all. So, that is another difficulty for using it high dimensional space. That is why not more than 20 attributes on dimension 20, it is advisable to use this technique. This is just an empirical observation. Memory based techniques, it means must make a pass through data points for each classification. So, these are several issues of k nearest neighbors, and as I mentioned, it is prohibitive for a large data set. So, this is the approach of nearest neighbor based approach. The other approach which I will be discussing now, that is called classification using discriminant functions. Now, in this case, we should consider a two class problems to illustrate. There are extensions to multi-class problems, but mostly in most cases discriminant functions are very easy to use for two class problems, and we can extend that discussions for multi-class problems. But in this particular course, we will be only considering two class problems. So, the problem statement once again let me revisit with respect to these two class problems. So, we have labeled data sets like there are n such training samples, each one has a label yi, each xi once again it is a n dimensional feature vector, and as I mentioned, xi is an n-dimensional feature vector, and yi there are two classes. So, we will be using class representation by this value of yi as +1 or -1. Then the problem of designing a classifier using a discriminant function is that this function needs to be designed such that if I use the if I evaluate the function at xi, then the sign of that value, which is either +1 or -1, which means positive or negative, should be the class identity. That is the definition of this problem. So, you should note that the decision boundary is given by g x equals 0. So, there is a boundary and which geometrically which partitions the space into two regions. So, in one part all the values, if I put the discriminant function there, it should give +1, the other part would be -1. Usually that is the scenario of discriminant functions, and on the boundaries only these values are 0. When we call this analysis as linear discriminant analysis, when this function g is in linear form, and it is a quadratic discriminant analysis when g being quadratic. So, the meaning of g is in linear form is that it is a polynomial of x of degree 1. So, x is a multidimensional vector. So, for each attribute which is taking part in the expression of functions, the polynomial degree of any attribute should not exceed 1. So, it is polynomial degree 1 and polynomial of x of degree 2 for quadratic. So, each attribute once again degree should not exceed 2. So, let us discuss a particular type a linear discriminant function or deriving of a linear discriminant functions from Bayesian classification approaches. So, we call it as linear discriminant analysis from Bayes classifier. So, the Bayes classification steps, as we have seen, given an input x, we need to estimate the posterior probability of yi given x for all I. So, note that yi in this case could be either +1 or -1. There are two classes. And then assign that value y k, that means kth value of the kth class. In two class problem, it is just there are two values, either y 1 or y 2 to x if it is maximum. Now, as we have already discussed that it is difficult to estimate this posterior directly, what we should do? We should compute the class likelihood and class prior from the data, which has been shown here, that probability of x given y I, that is the class likelihood of given the ith class y I, and the class prior is probability of that ith class itself. So, this is how posterior is related with them. And once again, just to stress that we are not going to compute probability of x, and that is why only computation of those two factors is sufficient to perform this classification. So, now let us assume this likelihood distributions are normal. We have discussed for naive Bayes classifier, where likelihood distributions we have discussed about the discrete and categorical classes, but categorical attribute domain attribute sets. But if I consider a continuous attribute value in a continuous domain space, the attribute value occurs, then we assume we can use parametric modeling, and let us assume that for every n dimensional n points, every n variables or n attributes, I mean it is in combinations is that n dimensional feature vector itself follow a normal distribution. So, here the independence of attribute sets are not considered. So, this is what a normal distribution in a multidimensional space is represented. Note here there are two parameters, though the number of elements in those parameters they are not single as it was for one dimension. One is m k, which is a k, which is once again n dimensional vector, which is the mean of the class, it is a vector, and S k is a covariance matrix of once again n cross n matrix, but which is symmetric. This is how the probability density functions in the multidimensional space looks when it is a Gaussian distribution. Just to simplify these expressions, we considered the denominator part as a normalizing part of this probability density function, and in this case this is constant. We are assuming that every class has covariance matrix. That is an assumption here. So, assume covariance matrices are the same, then only we can do this job. So, this is what S k equals S for all k. So, now we will be expressing this particular probability in the by using logarithmic operations, because the advantage of logarithm is that the comparisons of values in original domain can be carried out in the log domain, because those values are proportional to the log values itself, or log values are proportional to the original values itself. And as you can see in the normal distributions, the factor of one factor is an exponentiation operation. So, if you take the logarithm operation, so the power of that exponentiation operation will be basically computed, and it could make it, you could make it a linear form, or you could make it a polynomial form, rather it is not always linear. So, if I perform logarithm, so that is the advantage why you should apply logarithm operations over the probability values and compute the log probabilities or log likelihood values, whatever. There are different ways these measures are named. So, if I perform the logarithm of this expression of the posterior, so you know that it is probability of k, p k is the prior probability of class k, that is into that there is a product of p k and n x m k s k, that is the likelihood. So, once you take the logarithm, so it is log p k and this constant. So, the posterior is proportional to p k, that is the prior probability, into so posterior, the probability of k given x is proportional to this value. Now, once I take log of this operation, then log p k comes here, and from here we can see that this is a c, constant c. So, I should write here minus log c, because in the denominator, but it does not matter in our expression, because we can ignore it at it is not dependent on class for the in the comparisons of, because we have to find out the maximum of all log of these probabilities, and then assign that class which has that maximum value. So, in the in comparing those values, these constant terms will not matter, and this term is shown here, that is a logarithm of exponentiation operations, that would be coming there. So, this is the class. So, as I mentioned, we ignored this while comparing. You should note the correction here, this plus should be minus according to this representation. So, finally, it is sufficient to compare these values for finding out the class giving the maximum posterior probabilities. And we should assign that class which having the maximum value of this. So, we will see that how actually this will give you a linear form of function. We need to maximize this value. In between there are some steps, I will show them, and we can see that from the that was the operations I have shown, that is that there are two components in that operations which you need to maximize. One is the prior component, that log of p k, other one comes from the likelihood part. ignoring the constant terms, and if I expand them, just you can perform usual algebraic operations of multiplications using those matrices itself. So, these are the expansions of this term. So, if you expand it, it will be coming in this way. You can see that in my multiplications I have considered very standard algebraic operations. And this part is independent of class, because the covariance matrix is same for all the class, and given the data x. So, this is independent of class. Once again we can ignore this for comparison. And on the other hand, so that is why in this step we are not having this particular term. We have only 3 factors, but since S is symmetric, then actually this value and this value, they are same. So, simply we can add them. So, it should be minus 2, let us suppose m k transpose S inverse x, that is the value, and then if I multiply with half, it would be simply this value. So, let us show the algebraic operation. So, you can see that these 2 terms we can combine them into a single term, because they are the same. We simply can add them, and finally, we get this expression. So, in this expression, as it is possible to say that there are class dependent factors. These are all class dependent factors, but particularly this, for a discriminant function's point of view, this is a variable x in this discriminant function, and which is a linear form of a discriminant function. So, this is how we can derive a linear discriminant function using a Bayesian classification approach. So, this is a discriminant function for this class x, for class k, and linear discriminant function can be considered as difference of these two, because the sign of this you have to consider sign of g x. So, when g 1 x is maximum or greater than g 2 x, the sign would be 1 positive, and we assign it to class 1, and when g 2 is greater, the sign would be negative, then assign it to class 2. So, your linear discriminant function is g x, and which is as we can see, the form is a linear form. So, just to summarize this approach, that how linear discriminant functions could be derived following this Bayesian classification, what we need to do? We need to estimate different class priors, that is p k. So, for estimating class priors, you get the ratio of these two quantities. N k is considered as the number of instances in class k, and n is the total number of instances. So, that is how the class prior, and then given training data, estimate the means of classes and the covariance matrix of the data in this way, that this is m k, which is mean of samples in the class k in this expression, and covariance can be computed from the whole data. Now, this is one possible approach for estimating covariance. There are different other refinements are there also. So, I am just presenting it for the sake of simplicity of computations. So, you note m here is defined as a mean of the data. Say it is a overall mean of the data, it is not the class means. So, you obtain the discriminant function g x as we discussed and use it for classification. So, this is how you can perform linear discriminant analysis given the data points of two class problems. In the next type of classification, which is also a kind of a linear classifier, a special kind of classifier, or we can see that there are relationships also, and but we can have a different perspective from this. So, let us try to understand this particular classifier, which is called here perceptron. You can see there is a node and there is a computational block shown in terms of an ellipse. So, in this computational block it has its input where you are getting a feature vector as an input, described n dimensional feature vector x 1 to x n, those are the corresponding attributes in that feature vectors, and each attribute has a weight w I, and weighted combination of these attribute values plus there is a constant term which can be considered as bias w naught. So, this is a functional form. So, as such the function is also a linear functional form, as we can see, and the class, what we would like to do the classification, you have to once again it is the same, the sign of that. So, it is acting like a discriminant function. So, this z is acting like a discriminant function j x, and then sign of that will give you y. So, it is nothing but the same problem what I discussed in the previous example of deriving a example of linear discriminant analysis. So, this is also a linear classifier, but it has been shown with this perspective. It would be clear when I elaborate this aspect later on. Let me take a break at this point, and we will continue this discussion in the next lecture. Thank you very much for your attention.